recap a little bit of what we were doing last lecture. Go. You can see my shared screen. Okay. Right. Okay, so we were talking about composite systems, and composite systems basically means you've got more than one quantum system. In everything that we've been doing so far, we've only looked at just the one system, and now we're looking at what happens when we combine different quantum systems. So this is why I've got a picture of Alice and Bob here, because we've got more than one party here. Actually, by the way, can you see my mouse?
Yes.
Oh, you can. Okay, good. All right. Okay, so basically, okay, so this was the situation that we had before. We have each of these people, Alice and Bob, they have a D-level system, and then now Alice and Bob each has one of these. And basically what we were saying previously, if it was just like one of these people, is that the wave function is a superposition of each of these levels in one of them. Now, if you've got more than one quantum system, as we do here, then basically we have to look at every possible combination of the states. So for example, if you've got 2D equals 3, that means 2 3-level systems, then there would be 3 squared, 3 times 3 different states. Okay, so each of these is a distinct state, because basically in a combined system, you can think of these as all distinguishable, because if you say did a measurement, then you'd be able to tell the difference, of course, between any of these configurations. And the way that we mathematically write such a each one of these combinations is this tensor product. So I told you that sometimes I use this notation with the O times to say it's tensor product, but sometimes I just abbreviate the tensor product, or sometimes I just don't write the tensor product at all, and just consider that as one particular state. But then now there's 2 labels, because there's a label for Alice and Bob. So the most general state that I can write down is like this. It's basically runs over every single possible combination of the states. And the way that we can do that mathematically is just with this multiple sum here. So if you have a multiple sum, then that will basically go through every single combination, right, in the sum. And then each of those combinations has a coefficient like this. And in this case, there's like nine different coefficients. These numbers are all normalized. So as we have over here, these modulus squared adds to 1. And I could write this equally, this is just slightly different variations of the notation, but I can write it just like this, or if I consider the 2 things as one state, like this. They're basically all the same thing. Then this is just an example for 2 qubits. So again, it's just there's four states here, and the coefficients add to 1. And we looked at the case of independent states. So if you have 2 states and basically they have nothing to do with each other, then you can, in this case, the state would be described as just the tensor product of the individual states themselves. So if Alice has this particular state, psi A, and Bob has this particular state, psi B, then the state which is the composite state of those 2 is you just take the tensor product of both of these, and then the state eventually you can write it like this, and this is a specific form of state. So this is not as general as this thing that I wrote here, right? This A, NA, and B. This is more general than this one because this is a more specific example. You can't write all states in this form, but you can write all states in this form. And we discussed a bit about how to do measurements on composite systems. So in general, it works basically the same way as we used to. Basically, you just treat each one of these combinations as a single state. So I've written it as S0, 1, 2, 3 in this case for 2 particles, for 2 qubits. And basically each one of those outcomes could be observable. So, we could think of it as we're sending in 2 particles here, and then there's some measurement. And, this Sn could be actually in any basis. So remember, you can perform a measurement in any basis. And that's also possible when you do quantum measurements. The probabilities are the usual modulus squared. But the kind of more common situation that we might have is that each of these particles are measured individually. So say Alice measures her qubit and then Bob measures his qubit. Then there'll be 2 outcomes on each of their measurement machines. But then that still gives 4 different outcomes because there's basically 4 different combinations of the 2 outcomes on each. So there's still 4 outcomes like this. So either way you dice it, it's always like the same number of outcomes. In this case, we just measuring it individually, but you could measure it also in principle kind of as one whole system. And we looked a little bit about how measurement operators are made. Basically the way that they're made is like by combining the 2 operators for the 2 individual measurements in this case. So if you had measurement operators for Alice and Bob that were like MA and MB, then the measurement of the composite system you would make by this tensor product of the operators. And so, for example, these would be like 2 by 2 matrices, right? But this would be a 4 by 4 matrix because you've taken the tensor product of the matrices. And yeah, so for example, you could write out the 4 different possible projectors that you can have according to these different labels N and M, and they would look like this. Okay, and so we went back to the independent state example and looked at how a measurement of that type of state actually would work. And basically what we expect here is that if these particles are supposed to not have anything to do with each other, then the probabilities that you should get for say Alice measuring 0 should be exactly the same as if basically you sort of ignored this second particle, because if they're independent, then it should sort of have nothing to do with each other, right? So we worked out that the probability in this case, so if we treat it as a composite system and then perform the measurement, we're supposed to get, well, we do get 4 measurement outcomes. But if we say are only interested in the case of, say, Alice getting 0, then what we'd have to do is to add the probabilities for these 2 outcomes of Alice 0, then Bob 0, and then Alice 0, and then Bob 1. And then so what we did was to calculate the probabilities of those 2 cases, and we worked out that indeed it doesn't depend upon anything to do with Bob's case. And basically you get the same result as if Bob was not there. So, I think I told you a little bit about why this is why in when you write down a wave function, you don't have to take into account the wave function of the entire universe, because basically most of the wave function would be in this kind of independent state kind of type of wave function. So anything that's happening on Jupiter or somewhere very far away, the wave function of all that stuff is basically a tensor product of that. So you can include it, but it's not going to make any difference to the measurement that you're making, like in the lab right here. So that's why you can just omit it, or you can include it. It wouldn't matter. No. This basically shows that it doesn't matter. Okay, so I think that's more or less where we've got up to. Everybody fine with the revision part? Okay, yeah. So then just sort of continuing on from basically that same point. So for example, if you so if you for example, let's say that you were going to actually not even measure Bob's case at all. So in that case, so in the previous slide, what we actually did to measure Alice and Bob, but then basically ignore Bob's measurement because it wasn't really important, or all we really cared about was what Alice was going to get on her side. Now, suppose you didn't even measure Alice's you didn't even measure Bob's case, then what would the measurement operator be in that case? Well, it would look something like this. So this would be perhaps I should have written the Alice here just to be clear. So that's basically Alice's measurement, and again we've got this four-dimensional matrix, which is supposed to be our measurement operator. And basically what this would mean would be that so the identity matrix on Bob's side, this is the identity matrix like this. And then on Alice's side, say we're looking at a particular measurement of the zero state, right? So basically what this say we're doing the case n equals 0. So in this case, the total measurement operator would kind of look like this, and this is a tensor product. And so for example, this would be equal to something like this, plus 0, 1, 0, 1. And if you like, we could write it as a 4x4 matrix, and suppose we make the ordering of these matrices like this. In this case, basically what this matrix would actually look like, this is supposed to be 0, would be basically like the first two are 1, this is 0, this is 0, all the off diagonals are 0. So this would be kind of the 4x4 matrix that you'd be doing, right? And if you perform the measurement on Alice's side, and suppose we again have this independent state here, right? So this state here is again this independent state, so it's just like a tensor product of the two states. Then basically when we do our measurement, when we apply our measurement operator to this state, then basically what's going to happen, and you can do this in multiple ways, but this is actually probably the easiest way that I've shown you here on the slides, is that basically because when you have this this tensor product here, essentially what happens is that basically this is Alice's side, right? And this is Bob's side. And so basically the operator on Alice's side just gets applied onto Alice's state. The operator on Bob's side just gets applied to Bob's state. And you can basically work out the result like that. Sorry, my pen doesn't really work super well, so I hope you can still read it. And so when you apply the measurement operator to say this state here, then you'll get this measurement operator applied to Alice's state, the identity operator applied to Bob's state, and of course the identity times any state is just the same. And then you have basically just this state, which is the measured version of Alice's state times Bob's state. And then you can work out the probability by just doing the usual thing that we do, which is we take the inner product of this state, the thing that we just calculated, and then take the complex conjugate transpose. So we calculate this quantity here. Now, again, when we do the tensor product, we can just more or less just, well, Alice's side just talks to Alice's side, and then Bob's side talks just to Bob's side. So basically what we'll have is just from Alice's part of the wave function, this will give this term here. And then from Bob's side of the wave function, this will give this term here. But then this term is always normalized, which gives 1. And then you basically end up with the same quantity as you did for Alice's. Well, as if Alice just made a measurement on her side. And then the new state is basically, again, you just have to take the state that we calculated, over here, whoops, over here. And then we just normalize the state with the probability that we calculated in the second line here. And basically what you see here is that, this Bob state here, nothing really happens to Bob's state. It just sort of goes along for the ride, and you basically you still have that there at the end, but all the action is taking place on Alice's side here, and this is what we already saw previously with the single system case. So basically, what happens with this composite system example is that if you have independent states and then this measurement is independent also, then the second part of the system, basically nothing happens to it, and you can more or less just ignore it. Okay, so I hope that makes sense, or is there any questions at this point? I think people are looking a little bit confused. So let me how about I redo this calculation in terms of the matrix, just using a matrix, and then just sort of to reiterate the same point. So okay, so yes, sorry, what's that? I think you put yourself back on mute.
Hello. Yeah, like what is the, like, why we have this cross tensor product, the identity matrix?
Right. So when you I guess what I'm trying to tell you in this slide is, so how do you construct the measurement operator for the for the composite system, right? So if you want to measure like say a two-particle system, then that means that, okay, well, maybe I'll just sort of give you have another go at this, right? So for example, if you are like what we were used to before is, for example, let's say we have just the measurement operator for part A, and for example, let's say that we were going to measure in the Z basis. So the measurement operator would just be the projectors for this one. Right? So for example, in terms of the matrix notation, say this guy here would be just like a 2x2 matrix, right? So it would be like this, right? And so when you try to measure just like one particle, that's the end of the story, right? But then what if you are trying to measure two particles? Well, what I'm saying is what we've been talking about is that if you have a two-particle system, then the wave function would in general be I can hardly write with this thing, it's so bad. Sorry, 0, 0, 1, 0. Okay, so basically in a two-particle system, we now have a four-dimensional vector, right? Okay, so if we've got a four-dimensional vector, then we need a four-dimensional matrix in order to do the measurement, because obviously the dimensions have to be compatible, right? So, okay, and then in terms of the vector notation, this would be, of course, just something like this, right? Psi 1, 0, sorry. Yeah. So basically, it's a four-dimensional vector that we need to, that we have, and so we need a four-dimensional matrix, right? Okay, so basically what I'm trying to tell you here is how do we construct that four-dimensional matrix? So in general, this would be basically the way that you could do that is to, well, you could have MNA. Maybe I just have to write it slower and then the computer can. Okay, so in general, it would be written like this, right? So you have a the tensor product of two of these measurement operators. So each of these ones are actually like 2x2 matrices, right? So this one, sorry, not product symbols. And when you take the tensor product of these two things, then you will end up with a 4x4 matrix, right? So for example, let's start with n equals 0, m equals 0. Then essentially what we've got here is 0. Right, so this is the thing on Alice's side, and this is Bob's side. The next one would be 0 and 1. Okay, so this will be n equals 0, m equals 1. 1. Okay, 0, 0, and then 1. So this one would be 1, 0, and then this would be 1, and then 1. Okay, and then this is a 4x4 matrix because, well, let's just look at the first example here. this one. For example, this one is the same as the state. So in my sort of one of my alternative notations, this is like Alice in the state 0, Bob in the state 0 like this. And I can write that also in matrix form like this. Okay, so all these are off diagonals of 0. Okay. Okay, so everybody follow me so far? Okay, right. So if you so then so that's the more general situation. Now what I was just trying to say in the previous slide is, so what if you didn't really perform a measurement on, say, Bob's side? Then, then what would happen? Because clearly in this situation, what seems to be happening is that Alice is making a measurement here, right? And then Bob is also making a measurement here. So in this case, basically both Alice and Bob are making measurements. And so that's why we basically ended up with this kind of combined measurement operator, right? But what if Bob doesn't make any measurement, right? So, I mean, that's a perfectly, possible situation, right? So basically in that situation, what will happen is that the measurement operator in that case, because Bob doesn't really make any measurement, it's going to be just, well, so this is sort of the combined system. The measurement operator, and then this is for Bob, right? In this case, because Bob does nothing, the operator corresponding to doing nothing is actually just identity operator, because doing nothing is identity. So so in this case, essentially the so if we there's only really kind of two cases here. So so n equals 0 would mean 0, 0. And then the identity operator is 0, sorry, 0, 0 plus 1, 1. And this is 1, 1. And then this is the n equals 1 case. And then if we wanted to write this in terms of a matrix, then, well, okay, so this will be 0, 0 plus 0, 1. Okay, this guy would be 1, 0 plus 1, 1. Then, for example, if we wanted to write the matrix of that state, it would be 1, 1, 0, 0, and all these off diagonals 0. And ordering of these things, I'm assuming, is like this. So this is just a sort of a second example, I guess, of the more general case of in case Bob doesn't do any kind of measurement. And so we just go back to whatever I had in the slides here. So so basically that's basically what I was trying to tell you just here. But then I just give a particular example here of, so what if that measurement operator where we just Alice does the measurement gets applied to this particular state where we have this independent state, right? So I guess maybe, yeah, maybe in this slide I tried to introduce too many things at once. So so basically, the first point that I kind of want to make here is that, okay, so in the case that Bob doesn't do a measurement, then this is what the measurement operator would look like. Okay, so that's basically the first point. And then maybe the second point here is just a kind of an example where, okay, so if I apply that measurement operator where Alice is the only one doing measurement, and then I apply it to this independent state, which is not, again, not a general state, but just a particular state, then this is the result that I would get. And basically what this is showing is that you get exactly the same result as what we previously saw, which is that the probability just simply is this thing, which we already saw previously, and the new state here is this thing, except it's just got this Bob state floating around, which basically doesn't really take part in the whole calculation, but it's just sort of sitting there. And basically the results are very similar to what we had previously without the composite system. So so perhaps, I think I was trying to introduce, I was maybe going through this a little bit too fast in the way I wrote these slides, but the main points are just, well, this is how you construct the measurement operator if, Bob does nothing. Okay. So any further questions?
How to write cat00 outer product bra00 as a matrix?
That's easy. So cat 00, sorry, 00 bra 00, like this, right? How to write that as a matrix. So it's always that this is the matrix element. So essentially, when you write this, there are like four different states here, right? 0, 0, 0, 1, 1, 0, 1, 1. So you can tell it's like a 4-dimensional thing, right? So this one, we can just, I'm just writing this here as a guide to tell you like which rows correspond to which state, right? And the columns are the same. Well, I suppose I could write this as a so hold on. Yeah, so okay, I mean, maybe just to be very pedantic or very, right. So I think that's right. So basically the rows going up and down correspond to these kets, okay? And corresponds to the kets because the kets are the vectors, and when you have a vector, it should be the vertical ones, right? Now the bras, these are the conjugate vectors, and so these should be the ones that are horizontal, okay? And so basically what you can see here is that this is a combination of a ket and a bra here, right? And basically, if you have such a term like this, then implicitly there's a 1 factor of 1 here. So the weighting of this term is 1, and basically all the other terms are not present, so they're all 0. So basically this term is 0, and then all the other terms are all 0, right? So that would be the matrix, how you would write down the matrix for that particular term. But you can do it always for any term like this. You just have to look at the correct You know, so, you know, if you had the term, I guess, 0, 1, you know, 1, 1, then of course that term would just be like, well, like here, right? So this would be the term there. So it's supposed to be 0. So you would put that element there. Okay. All right. Any other questions? Okay, then okay. Right. So we'll do a couple of examples after this. So hopefully we can make sure you get the hang of all this. Examples are, yeah, coming up shortly. Okay, well, perhaps thinking. Yeah, okay. Well, I don't know. Maybe so that you get the hang of this, maybe we can just sort of make up an example now so that you don't lose anybody. So, okay. All right. So suppose we have something like this. So suppose we have let's see, I'm just thinking what example to do. All right, so suppose Alice is going to measure in the plus minus spaces. Okay, and then Bob is just going to measure in the 0, 1 basis. And then suppose we have the state, well, just to make our lives easier, why don't we just have something that doesn't involve all the terms. Okay, suppose we have that state there. That's supposed to be a beta there, alpha and beta coefficients. Then let's try and work out basically what is the measurement probability and outcome of, let's say, Alice getting plus. So this one, so Alice getting plus, and then say Bob getting minus, these two. Okay. So basically what we would do in this example would be, so firstly we can construct the measurement operator for this process. So this measurement operator is going to be MA, and then for this plus example, times by MB 0. Okay. And so let's just put those in. So it's plus 0 like this. Okay. And okay, and then we can rewrite this, well, just to combine the notation a bit. So okay, so maybe I'll use that second notation like this. Okay, no, actually I won't do that. Okay, or how do I want to do this? Yeah. Okay, well, I guess we can just leave it like this. Okay. All right, and then so the first step into working out, and say, we had to work out what the probability of this particular measurement outcome was. So what we do is we apply M to this state psi. Okay, and then so we've got psi times 0, 0. Okay, and then we can go back to the tensor product notation for this one. So this is Alice has this state 0. Bob has state 0 here. Bob has state 1. Sorry, Alice has state 1. Bob has state 1 here. Okay, and then what we do is basically just expand this whole thing out. And so this side on Alice gets applied to the state on Alice. And this operator on Bob's side gets applied to Bob's state. And then similarly for the second term, like that. Okay. So what's going to happen is, so let's just pull out this constant coefficient out the front here. And then we have plus, and then we have the inner product between plus and 0. Okay. And then we've got tensor product that with 0. So we're doing the second term here, 0, and then 0 inner product with 0. Okay. So that's the first term here, right? So the first term that we've just kind of identified here, this is the, we've just multiplied this measurement operator with this first term. Okay, and then let's continue on with the second term. So I didn't close the brackets. The beta, and then the plus operator gets applied to this one plus, and then 1, and then tensor product of that with 0 with 0 inner product 1. Okay. Okay. All right. So now we can simplify a couple of things here, because so for example, what is the, does anybody remember what the inner product of this plus state with 0 is?
One over square root 2.
Yeah, 1 over root 2. That's right. So this thing here is 1 over root 2. What is inner product 0 and 0? Yeah, just 1. It's just 1. Here we've got, again, inner product of plus and 1. What is this factor going to be?
Minus 1 over square root 2.
Yes, 1 over square root 2, but no minus.
Okay, no minus, no minus.
Yeah, no minus, because the plus state, so the definition of plus state, maybe I should have written it just
It's just plus.
yeah, it's 0 plus 1, right? So both of them have a plus sign, so there's no minus signs anywhere. And then 0 overlap, or 0 inner product with 1.
0.
Yeah, 0. So actually this whole second term, this is 0, right? Actually, this whole second term is 0. So that just disappears. And we can just sort of collect the terms here. So we've just got 1 over root 2, we've got 1 here, and then alpha, so it just becomes alpha over root 2, and then plus state tensor product with 0. So basically, the thing that you get at the end here is just the plus state and zero, and just with with any measurement, you basically just always get the state that is that outcome, which is it's almost it's kind of a bit of an obvious statement, but I'm saying, I said Alice gets the plus state and Bob gets the zero state, right? And so obviously at the end of that process, if that's the process that we're looking at, that's the state that we should get, right? So that's exactly the state that we have. We have this zero state and sorry, we have the plus state on Alice and then zero state on Bob, which is that. But the important information here, so this is sort of obvious in a way because that's the case that we looked at. But then this is the coefficient of that, and from the coefficient of that, maybe I squeeze it into this slide just so that. So the probability of this happening is so state measurement. Wow. Okay, maybe I use my finger. I don't know. Oh my gosh, it's getting worse and worse. Measurement operator state. And basically, in this case, it's just going to be alpha star over root 2, and then plus product 0, alpha over root 2 plus 0. And the plus state and the zero state are normalized. So eventually, the states are just going to give 1, and we will have alpha squared over 2 is the probability. All right, is that fine for everybody? Okay, good. All right. So just resuming a bit. All right, so that's how measurement operators work. Now let's talk a little bit about how observables work. So remember, the deal with observables is that essentially they're averages, right? So when we did observables, what we were doing was, the measurements are giving probabilities. So just like we calculated in just that example right now, so we get some probabilities, and then observables are just that, but then we use those probabilities to average over something, okay? So average over some quantity, and the value is given by, whatever the observable is, right? So in this case, the values of the observables just maximize this again. Okay. Oh. Yeah. Okay. So in this case, the values that we're talking about are these little r's here. That's the value that is going to be given, and so basically in this composite system case, everything looks exactly the same, except that all the states have two variables here, because there's Alice and Bob, and each of those different combinations are going to give different particular states. And so this is the state that we have, and then if we did a measurement in this a different basis, say this M basis, and this M basis might not be the same as the N basis, but we saw that that doesn't really matter. Actually, in the end, all we have to do is just put it into this formula, sandwich the observable by the states, and then, you know, we always get the average that we're interested in. And the story is basically exactly the same. Just, you know, you just got a whole bunch of double sums instead of single sums. And all these things like A, which is the wave function, and then the R, which is the observables, you know, they've all got two labels because there's like all the different combinations, but apart from that, it's exactly the same. So basically, we can view these coefficients. Remember these B coefficients, they came up when we like did that basis rotation into the, so when you rotate the basis of this wave function so that it goes from the basis, this original basis, into the basis of the observables. So if you go from the N basis to the M basis, then you'll get a bunch of different coefficients so that, you know, our wave function is written like so our wave function would be written as MA MB, the B M A M B. Yeah, so our wave function in the M basis would be written just like this, and we can get an explicit formula for that just using exactly the same arguments as we did previously. And so we can go from the N basis to M basis like this. And then basically these things here are just your probabilities of getting each outcome, MA and B. And then the R's are just the values that you average over. So we can calculate averages in exactly the same way. Okay. Delete this. Okay. All right. So now, okay, yeah. So in a similar way to, we had like independent measurements, we can also have independent observables. So if say Alice and Bob, so, you know, they're doing individual measurements, like, you know, Alice is measuring her particle and Bob is measuring his particle, right? So if you can do independent measurements, then definitely you can assign observables that are like, you know, on each side, right? So in this case, Alice, whenever she's going to measure this state MA, she assigns a value S to that case, right? So we can make a matrix that's the observable for Alice, and this is what we already encountered before. And now if Bob also has some kind of observable and measurement combination like this, so he's also got his observable matrix, and then we can make a joint observable just by taking the tensor product of those two individual observables. So for example, in the qubit case, this SA would be like a 2x2 matrix, SB would be like a 2x2 matrix, but then this combined thing S would be like a 4x4 matrix. So we could write this in this form, where basically the combined observable in this case is just the product of these individual observables. So SMA, S tilde, MB, those two things, just the product of those two things are the combined observable. Okay. And again, this is like a more specific case of like a more general observable here, because of course, you know, you can have any number of any possible observable here, just because these are like the full number of degrees of freedom. Now this is a more restricted type of formula, because anything of this form can be written like in this form, but not the other way around. Okay. Okay. Any questions on this slide? Okay, then all right, so then let's just look at a few more examples, or let's look at a couple of examples of this calculating observables, because actually this is a pretty sort of standard or important thing that you need to be able to do. So let's just make sure that you can do it. So the case that we're going to look at is like this. So we've got two qubits again. And what we want to do is to evaluate Z1, Z2. So this combined observable. So Z1, Z2 base is, another way of writing. So Z1, Z2 means the same thing as Z1 tensor product Z2, same thing. I just omitted the tensor product symbol there. So this is like a 4x4 matrix, basically. And here's the state, just a general state. And how do you calculate this average value? So the average value, again, you calculate according to this expression here. Okay, so I've basically got the answer there, right there on the sheet, but let me just try and, well, actually, I don't know, maybe, well, let me attempt to go. This is what I would normally do in class, but my writing here is a bit compromised. But okay, so so the thing that we want to calculate is Z1, Z2 average. So that's the state that we want to calculate. So this is just according to the formula Z1, Z2, and then the tensor product is like this. So this thing is basically, again, it's a row vector times by a matrix times by a vector. And in this example, this is like a four-dimensional vector. This is a 4x4 matrix, and this is a four-dimensional row vector. Okay, so so that's basically what we're doing. So let's just break this down into a few parts so that we just make our lives a bit easier, so we don't do that whole thing all at once. So let's just try and calculate what Z1, Z2 times by this state here is, okay? Okay, so this is the way that I would do it. So, okay, I'm omitting Z, sorry, the tensor products. And so we've got A00, 0, 0, A01, 01, A10, whoops. And A1111. Okay. I'll make this. Okay. All right. And basically the idea here is that so remember I've sort of omitted the tensor product. So, like for example here, what I really mean by that is actually Z1 tensor product Z2. And what I mean here, for example, is 0 tensor product 0. And basically the rule with these tensor products is that Alice's operators only operate on Alice's states, and Bob's operators only operate on Bob's states. So basically all you do is just apply these things in parallel. Okay, so just that part just gets applied there. That thing gets applied. Sorry, I shouldn't say that in this. So Alice's operator just gets applied to Alice's side. Yeah. So yeah, Alice's operator just gets applied to Alice's state. Bob's operator gets applied to Bob's state. Okay, and so we know how Z works. So basically, what Z does is to just put a minus sign on the state if the state is 1. Okay, that's our definition of Z. What we had before. It's a Pauli matrix like this. So for example, in this particular one, because Z acting on both of these are 0, so basically there's no change in the sign of this state. And of course, the state 0, 0 is just going to remain as 0, 0. And there's no change in that. But some of the other states will have a change in sign. So which states do you think will change in sign?
One.
Could you just repeat that? Just because...
It's cat 1 1.
Cat 1 1. Unlucky because that's actually the only one that doesn't.
Like 0 1 1 0.
Exactly. Yes. Yes. So
1 1 2
yeah.
minus cancel.
Exactly. Yes. So what's going to happen is with Z1, Z2 applying on 1 1 is that so Z1 applied on this state would give a minus sign, but Z2 applied on 1 also gives a minus sign. So it'll be minus 1 squared 1 1, but then minus 1 squared is 1. So in fact, that one is another state that does not change in sign. However, the states 0 1 and 1 0, okay, 0 1. 0 does not pull out a minus sign, but 1 does, right? So this one will have a minus sign on it. And then similarly for 1 0. So 1 0 will have a minus sign. So basically what will happen here is that there'll be an extra minus sign here and here, okay? And then these ones will remain plus, and this one will also be plus, okay? Okay, then, so given that, let me make some space. Is there a faster way to do this? No. Okay, so we worked out what happens after Z1 gets applied. I can't change the color back. Okay, here we go. All right, so now let's just do the second part of the calculation, which is to take the inner product of the resultant state, Z1, Z2 with psi. Okay, so we've got our state, which is alpha 0, 0 star plus, oops, alpha 0, 1 star, alpha 1, 0 star, and alpha 1, 1 star. And we take this state, the thing that we just calculated, and make sure we put in the correct signs. So this one will be minus. This one will be also minus. And this one will be plus. Okay. Now, we just have to calculate the inner product. Trying to, yeah, here we go. Okay, and then, so basically the only terms in the inner product that are non-zero are like the ones where it's the same state, right? So like this one and this one, this one and this one, this one and this one, this one and this one. So the four states that we're going to get are A00 modulus squared minus A01 modulus squared, A10 modulus squared plus A11 modulus squared. And basically that's the final answer. So that is.
Professor, I just want to make
Yeah.
sure for the conjugate, we don't need to care about the signs. For
Right, yeah. Okay, let me just go back to that. Yeah, so when you do the conjugate, where's my pen? When you do the conjugate here, yeah, it's purely taking a complex conjugate transpose, and you don't change, you don't fiddle with the signs, right? So you just take these coefficients like A0 and these ones, A10, just take the complex conjugate, and then that's it, right? And then for the actual states, the kets turn into bras, and then that's it. And don't mess with the state any more than that. Now, the only reason why these ones had an extra minus sign here, for example, and that's basically because of the action of this operator here, right? So if that operator Z1, Z2 wasn't there, then all these would have a plus sign. And basically, in the final result here, you'd just have A00, A01, but then with a plus sign, A10 with a plus sign, A11 with a plus. Everything would have a plus sign here, but then it's a normalized state, so that would actually always be equal to 1, right? But now with the minus signs, it might not be equal to 1 anymore. Yeah. Okay. All right, well, I think maybe we should leave it there because I think all we've got here is another example, and maybe that's a good place to recap for next week. So, okay, any questions or anything you want to ask for today? No. Okay, then don't forget to send your homework today. I think. Oh yeah, hello. Yep.
when are you planning to send us the solutions for the homework?
Sorry, for the submissions of what?
The solutions of the homework.
Oh, okay. Yeah, all right, fine. I'll solutions for the homeworks, right?
Yeah.
Ah, right. Okay. Well, we've only done 4. Well, after today we'll have done 5.
I just kind of wanted to have like a formal like
Hmm.
like steps for each questions.
Ah,
Like that.
okay.
Yeah.
Well, okay. I mean, actually, my notes are not really super like it doesn't totally follow the questions as they are now. I'd have to like kind of separate out the ones that we haven't done, the homeworks that we haven't done yet. So, well, let me see if I can do that. I mean, you know, if you had them like by I guess next week, would that be all right? Because then you'd have like homework 6. I mean, actually, I usually write down in your homeworks like
I see like
basically like
how I
the
got it
answers.
wrong.
So yeah.
Yeah, I see. Saw like how I got them wrong. It's just like I kind of wanted to have like
Mm,
like a formal steps to
mm,
write each kinds of questions like correctly.
right. Well, yeah, I mean, in your case, I think, you know, you're doing totally fine. I mean, the only thing I think you just didn't take the complex conjugate sometimes, and then you got some questions wrong just because of that one error. So I think there's like, you know, I don't think there's any real problem you should be worried about actually. But how well, yeah, okay. How about I try and upload the solutions maybe by next week, because then I think that's a easier break in terms of how I've got the solutions there. So
Yeah, just like a couple days before the exam will be fine.
okay, all right, okay, yeah, and I haven't forgotten about the sample exam from last year, so
Mhm.
I'll try and do that soon. Yeah.
Thank you.
Okay. All right. Then I will see you all next week.
And I think I
Oh, yeah.
send the homework to you, right?
Yes, I got
Yeah.
your one, yeah.
Yeah.
But
Thank you.
yeah, so for everybody else, please send it and then I'll...
I think I sent it to you last night.
Oh, okay. All right. Maybe I didn't see it. Okay. All
Did
right
I?
then.
Yeah, I did. I think I did, but it,
Okay.
like,
All right.
didn't-
Sure. No problem. Okay. Yeah. All right, then maybe I've got everybody's then. All right then. Okay. See you later.
I
Okay. Bye.